Now that we've seen the idea of measuring big O notation, different classes of complexity, what I want to do is look at some examples. Here are the list of classes in order of increasing complexity. And my goal here is to show you examples from almost all of these classes, partly so that when you come across a new problem, you can recognize some of the characteristics of that class. There are certain patterns that are going to put an algorithm into a class like polynomial or quadratic, or into a class like linear, or into a class like logarithmic. And so the goal is to both let you see how we analyze algorithms, to say what class they belong to, and to let you see the characteristics so that when you're creating your own algorithm, you have a sense of how difficult is it going to be to solve this problem. So we'll see examples of order 1, or constant running time complexity, order log n, logarithmic, order n, linear, order n log n, often referred to as log linear, order n to the c, which is polynomial, where c is a constant, so n squared would be quadratic, n to the third would be cubic, and finally order c to the n, where c is a constant, which is an exponential running time algorithm, and the most expensive of the classes that we are going to deal with. Let's start with the simple ones first. Constant complexity algorithms. There are very few interesting examples of this, unfortunately. They're the nicest ones because these are cases where the complexity is independent of the input. It's going to take the same order of time no matter what the input is. While there are very few interesting algorithms in this class, often pieces of other algorithms do fit here, and we're going to use that to help us reason about the complexity of other parts of algorithms. Note, by the way, that one can have loops or recursive calls and still be in the constant complexity case. It's simply that the number of iterations or calls in that instance will be independent of the size of the input. We're not going to show you examples of these because they're mostly pretty boring. Logarithmic complexity, on the other hand, is something that's going to be very nice. These are very efficient algorithms. And here, these are algorithms where the complexity grows as the log or logarithm of the size of one of its inputs. Standard examples: bisection search, a binary search of a list. Anything that divides the space of the search in half at each step is a nice characteristic of a logarithmic complexity algorithm. So let's look at a little example here. Here's a very simple example. It's a little program that's going to take in an integer and convert it to a string. And there's standard ways of doing it, but in this case, it's going to run through a little loop to do that. So what does it do? It creates an internal variable called digits, which is a string of the digits from 0 to 9. And then it does the following. Given that input, which is an integer of some size, if it's 0, we just return the string 0. Otherwise, we set up a little loop. We set result to be an empty string. And then we run through a little while loop here, where we take I, get its remainder base 10, which is basically the lowest order digit, and then index into digits at that point, which retrieves that character of the string, and we add it onto result. And then we divide I integer-wise by 10. We shift right. So we're literally going to take each digit in turn, figure out what the character as a string is representing that, and then add it into the result. I don't care what this does. There are lots of other ways to do it. What I want to do is use it as an example to understand the complexity of this algorithm. So let's look at that. There's my code. And what do we know here? We know that we really only have to look at the loop because there are no recursive function calls here. I'm not calling int to string multiple times. Everything's in the body of this code. What else do I know? I know, and I'm going to actually jump ahead slightly here, I know that these stages here are constant. I only do it once. We've already seen in our earlier analysis, they don't matter. So all I have to do is look inside of the while loop. And in that while loop, the things I'm doing are a constant number of steps. So inside of the loop is constant cost. Therefore, all I have to worry about is how many times do I go through the loop? And the answer there is basically how many times can I divide I by 10? Because each time through the loop, I reduce I by a factor of 10. And that is just logarithmic. It's log base 10 of the size of I. So this is an instance of a log complexity algorithm. Now you might say for a second, wait a minute, isn't it linear? And it is in a funny way. It is linear in the length or the size of n, but it is log in the number of digits in n. And since I want to measure this in terms of the number of digits in n, sorry, I'm going to say that better. It is linear in the number of digits in n, but log in the size of n. And since I decided to measure this in terms of the size of the input, I would say that this is an example of a log-based algorithm. And the characteristic is I'm reducing the size of the problem by a constant factor at each step. Okay, linear complexity. Still pretty good because it's pretty efficient. Examples you've already seen. I want to search a list in order or in sequence to see if an element is present. It's linear because I'm going to walk down the list in turn looking at each element until I find whether that element is present or not. A nice example of a linear complexity search. Another nice example, I want to add up the characters of a string, which I assume to be composed of decimal digits. So I've passed in a string. It's a string representing a bunch of numbers or decimal digits. I want to add them up to get the sum of what those digits comes to. Again, a simple example, but it's going to let you see the characteristics of a linear class algorithm. So there's a simple piece of code to do that. Passing in a string s, I initialize a variable val to 0 initially, and then I'm going to run through a loop where I take each character in s, which is a string, and I'm going to convert it to an int, add it to val, and when I'm done, I'm just going to return val. Simple algorithm. What I want you to see is the order complexity here. It's pretty obvious. What do I have to count? This is a constant time evaluation. Similarly down here, this is going to take constant time. Inside the loop is also constant. I've basically got a conversion to an int, an add, and an assignment, so it's 3 steps. All I need to worry about is how many times do I go through this loop? And the answer is however many characters there are in S, the string, so it is linear in the length of the string. Nice example of a linear time algorithm. Now, let's look at some examples where we actually have calls. And I'm going to start with an iterative algorithm, one that you've seen before, computing factorial iteratively. And to remind you, factorial of n is n times n minus 1 times n minus 2 all the way down to 1. Here, I set up an internal variable to be 1, and then I run a loop where I ranges from 1 up to n of simply doing the product of what I've already had times I and storing it back into there, and then I return the product. And again, the question is, what's the complexity of this? Well, it comes down to the same thing. The return is constant, the setting up a product is constant. What I want to measure is how much cost is there inside the loop, and I know that's also constant because it's just the same number of, in this case, 2 operations each time through, plus 1 assignment up here to set up I, so 3. So the real question is, how many times do I go around the loop? N. That's the size of my problem. So the number of operations, as we've said, inside the loop's a constant. We go through that thing n times. Therefore, this is just 3n, which we've already seen is the same as saying it's big O notation, order of n, or linear. So something that has a loop in it with a constant number of operations or work inside the loop, characteristic of a linear complexity algorithm. Okay, we got iterative version of factorial. What about the recursive one? Well, we've seen this as well. Remind you that the recursive version says if n is 1 or less, I return 1. Otherwise, I return a recursive call to the procedure with a smaller argument, and then when I get the result out, I multiply it by n, and I return that as a value. If you were to actually time these two, you probably would notice that the factorial version that's recursive is slightly slower than the iterative one, mostly because of the cost of setting up the recursive call. But we've also said that timing isn't the only thing we want to do here. It's really what are the number of operations we have to do. And here, this is still linear because the number of things I have to do to set up the recursive call are just 2. And more importantly, how many times do I call this function? I call it n times. And so again, it's order n, even though it's recursive rather than factorial. Again, the characteristic here is I'm doing a recursive call once per each increment in the size of the problem. And inside of that operation, I'm just doing a constant number of things. So notice, in an interesting way, both the iterative and the recursive factorial implementations are the same order of growth. It doesn't mean they'll take exactly the same amount of time on the same size problem. But since we want to measure asymptotic order of growth, as we let the size of the problem get really large, these both belong to the same class. They're linear. Now, the next level is what we call log linear. And we're going to see that many practical algorithms fall into this class. It's another nice, efficient class. And is very commonly used on things like an algorithm called merge sort. And I'm simply going to defer you. We're going to come back to that in the next lecture. But this will be a classic example of a log linear algorithm. And you'll see it in a little while.